In the last video, we ended by talking about working to connect our tangential velocity, our angular velocity, our tangential acceleration, and our angular acceleration with one another. Okay, and so this is what we're going to do in this video. And the way we're going to do it, let me just go over here and grab the picture that we started off with. And I'll just take this, drop that in right there. Okay. So one of the things that, and I'll just do this in a different color, but one of the things that that's going to connect these two is the idea of an arc length. And so our arc length is going to be defined like so. So we're going to have some initial position S and some final position S sub F. So now we're talking about this orange portion here. And we're not necessarily talking about what we were doing earlier, but it is directly connected. But I'm using this portion, so I'm using the bottom portion for a reason, okay? So just bear with me. Just bear with me for a moment. So this arc length here is just going to be delta S. And we want to know that both of these are vectors. So delta S is just going to be S final minus S initial. Okay? You guys follow that? So it's going to be from this, it's going to be a measurement from this position to this position. And it is a length. So it's going to be measured in meters. Okay? So we have our angle here. Our angle is, again, theta initial so I'm just putting this orange over it, just saying that it's also a part of this. Okay, so we can define, or we can define some things when it comes to this for small angles. So what I want to do now is I want to go ahead and define a triangle here. And this is our standard right triangle. Okay. Now, what I want you guys to imagine, you see this side right here, this Y right here, this side. If we understand this, we could just say that sine of theta initial is going to equal to the opposite side, which is Y, over the hypotenuse, which is R. Okay, so we have R right here. Let me say that R is right here. So all of that is great. The main thing that I want you guys to see is for a very small angle, let's just say that theta is very small. And now I just want to go to another page. Now that we have this information, I'm going to draw this triangle again. So remember, we have our triangle. We have our arc length right here. Okay. And we have our angle, theta. And I'm just going to call it theta. And I'm going to call this delta S. And we have our Y right here. This is a right angle. And this is R. We know that sine of the angle theta is going to equal to Y over R. Now, for theta being much smaller than 1, we can, and I'm putting those two less than signs there to indicate that it's much smaller, as opposed to just less than. Okay, so it's much smaller, or very near 0. Then we can make this assumption: Y is going to be almost equal to delta S. And I would rather put, let's just say in the limit, they will be equal delta S. So if we take the idea that everything is an approximation onto exactness, and we allow our brains to understand the the idea of infinitesimal, then this will be fine. So we're going to let this be the case. So that means that if the angle is much less than 1, then that means that sine of theta is approximately theta. Okay? So now we can substitute those things into our original sine equation. We can substitute them into this equation. So we'll end up with theta is equal to delta S over R. So now we can define our arc length in terms of R and theta. And our arc length is now delta S equals to R times theta. So that means now we're still working with our same, we've gone from rectangular coordinates to polar coordinates, and our polar coordinates are R and theta. And now based on our polar coordinates, we can actually define the arc length. That's really what we're saying. Now, if we look at the velocity along this arc length, we're going to have two different velocities, or we're going to have two, yeah, we could just say we have two different velocities, but we have an initial velocity here, and since it's an arc length, it's a tangential velocity. So I would just say our initial tangential velocity here, and then we're going to have our final tangential velocity here. So we're going to connect our tangential velocities to our angular velocities this way. So let's go ahead and do that. We know that delta S over delta T is just going to equal to our tangential velocity. We've defined this already many times, all right? We used X and Y and Z before, but we'll just say we use X and Y. So now this is going to equal to R, the change in R, delta theta over delta T. And just to be thorough, this could be written as theta delta R plus R delta theta all over delta T. But we're not considering a situation where R is changing. So there will be no change in R, so this piece is just going to go to 0. So we end up with R delta theta over delta T. This is our relationship to the tangential velocity. And this is going to be equal to, remember we defined angular velocity as delta theta over delta T, and we called it omega, so this is R omega. So this is our relationship here, and I'll just write it again. So how do you think about this? Well, if you have a certain amount of rotation coming from a wheel or a tire, then it's going to correspond to a certain translational movement when it comes to your, like, let's just say your car moving in a certain direction. Okay? So there we go. In the next video, we'll talk about our relationship between our tangential angular acceleration and angular velocity as well as angular acceleration.